In Chapter 18 of Categorical Data, we're going to look at the ChiSquare, which is a very popular non-parametric statistical test that is appropriate when data are in the form of frequency counts or proportions that can be converted to frequencies. By the conclusion of this lesson, we're going to determine when it's appropriate to run a chi-square test, identify the variables you can use, make sure that you meet the data assumptions for running a chi-square, interpret the test results, and write results following APA style. It's important to know that the statistical function for comparing categorical variables with each other is the chi-square. Sometimes it's written as a Greek letter. Most often you could associate it maybe with the fact that it's different than the hypothesis tests that we've learned, like t-tests or ANOVAs, because of the type of data we're using. Rather than using numerical scores that were on a scale of 0 to 100 and were a ratio level of variable, we're now going to be working with frequencies, which are nominal or interval level of data, or nominal ordinal level of data. It's important to know that each participant can only belong to one category in the matrix, and that the categories can't be meaningfully placed in order. So the types of variables we could use have dichotomous options. And so they are going to be gender with male and female, opinion, yes or no, attendance, present, absent, respondent type, early versus late. But then we can also look at categorical variables that contain more than two categories, and that is called the polycotonomous. And we can do that through the log linear analysis discussed in Chapter 18. Examples might be marital status, where we have single, married, separated, divorced, widowed. We have visual aids, meaning none, glasses, contact lenses. We have blood type, or we have age categories. And it just means that all of our data has been counted and divided into categories. And the chi-square test cannot work with parametric or continuous data such as height in inches or age as in just 98. It needs to be a range. And so, for example, if you want to test whether attending class can influence how students perform an exam using test scores from a range of 0 to 100, the data would not be appropriate for a chi-square test. However, if you want to look at whether attending class influences students' ability to pass the course, and you arrange the students into two categories of passing or failing, then you could use the chi-square test. Additionally, the data in the chi-square grid should not be in the form of percentages or anything other than a frequency, which is the exact count of the number of respondents for each category. The chi-square is appropriate only for nominal or ordinal data, and it can be used to compare your frequencies occurring among those categories. Before we can actually do any analysis, we have to know that we do not follow the assumptions discussed in Chapter 5 that are for parametric tests. You can't have normal sampling distributions because your variables are not continuous, meaning they're not measured on an ordinal interval or ratio level. But what we can make sure is that for the chi-square test to be meaningful, it's really imperative that each person, item, or entity contributes to only one cell of the contingency table. So therefore, you can't use a chi-square test on a repeated measures design. And with a 2 by 2 contingency table, no expected value should be below 5. And in the larger tables, like in the log linear analysis, when we're looking at associations between 3 or more categorical variables, the rule is that all the expected counts should be greater than 1, but no more than 20% of all of the expected counts should be less than 5. And if you have categories in your 2 by 2 contingency table with less than 5 counts, then you might need to consider using the Fisher's exact test for your analysis. And when 3 or more variables, the log linear analysis is done, you might need to consider a few different ways to work with your data. If you don't have 5 counts or more in each category, you can collapse your data across one of the variable, and that's just the one that you least expect to have an effect on the outcome. You could collapse levels of one of the variables. So when you think of marital status, if you know the majority are married, you could then collapse together single, divorced, separated, and other into a different category and just have 2 categories. But for log linear, you might need to make maybe 3 categories, like married, not married, other. And that would work really great for the log linear option. So think of how you could collapse down your categories to maybe just 3 options. For political parties, it might need to be conservative, liberal, and then moderate. You'd have to find a third category that's kind of in between to make that work. You could just collect more data from your study participants, or you could just accept the fact that you're going to have a loss of power because of how few counts you have for all the categories. And if you want to collapse your data across any one of the variables, then you're going to have to meet certain criteria. The first thing you're going to do is make sure that your highest order interaction is non-significant, and then at least one of the lower order interaction terms involved in the variable to be deleted should be non-significant. So work with the items that are non-significant if you want to collapse your data. Your chi-square organizes your data from the categorical variable into just one table, and it compares the categories with each other. And so in that table, you're just going to see your frequency counts that are for observed and expected values. But for the Pearson chi-square test, what you're going to have to remember is that we're actually looking at the null hypothesis stating that there is no relationship between the 2 variables, that our 2 variables are very independent. And what we're doing is looking to see if there is a relationship between those variables. So we do that by comparing the frequencies we observe in certain categories to the frequencies we might expect to get. And our model is really based on our expected frequencies. And so here are the formulas from our textbook that might help you understand those concepts of the observed frequencies and the expected frequencies and how those work together. Really, you're not doing any of the math, so as long as you understand the concepts and running the chi-square and SPSS, you'll be great at being able to interpret the information and writing it up appropriately. One thing you need to be aware of is that the Yates correction is a correction made to account for the fact that the Pearson's chi-square test is usually biased toward a 2 by 2 contingency table. It creates this bias in which it does an upward bias, making the results actually larger or more significant than they actually are, than they should be. One big problem is that if your significance values are just too small, you can have a type 1 error. That's a real problem in your data. And so what you can do is with the Yates continuity correction, you actually calculate your deviation You don't care whether it is a positive or negative number. You subtract 0.5 from that value, and then you square it. And then you have the Yates correction, and that actually lowers the value of your chi-square statistic. Therefore, it makes it less significant. And although that really seems like a great solution to your problem, there is a lot of evidence that shows that this overcorrects and actually produces chi-square values that are too small. And we see this a lot in medical research, and our journals as well as statisticians are warning individuals to ignore the Yates correction and not to use it. So let's take a look at how we can do a chi-square test using a weighted cases situation and to measure an odd ratio. And so the task comes from task 6 of our chapter, and this is what Andy wrote. I wrote much of the 3rd edition of this book in the Netherlands. I have a soft spot for Holland. I noticed cultural differences to England. The Dutch travel by bike much more than the English. I noticed also that many more Dutch people cycle while steering with only one hand. I pointed this out to one of my friends, Bridget Mayer, and she said that I was being crazy and that the Dutch people did not cycle one-handed. Well, several weeks of me pointing out at one-handed cyclists and her pointing at two-handed cyclists ensued. To put it to the test, he actually counted the number of Dutch and English cyclists who rode with one or two hands on the handlebars, and so we're going to figure out whether Bridget or Andy is correct. And so the first thing we need to remember is that we're going to use a data set called handlebars.sav, and it is designed that we're going to use the weighted cases command in SPSS, which is just one of the ways that you can enter data in SPSS. It's not very often used, especially if you're collecting your survey data using an online system like Qualtrics, or if you're manually entering your data from a paper survey. You tend not to see that in agricultural communications, agriculture education, or extension education. But I want to demonstrate for you how it's used. Because basically it just has all the frequencies already collected for each one of the variables, and it simplifies how many cases you have in the SPSS file. And then we're going to just make sure that we drag our frequency variable into the frequency variable column, and then hit OK and save that so it works appropriately. What we're going to do now is to demonstrate that. So I'm in the handlebars. This is our data. You'll see how much more condensed it is, because see here how many people they collected data from. It just prevents having a lot of cases. But like I said, if you're doing your data in Qualtrics, you're not going to get it this way when it exports. So I tend never to use weighted cases. But what you're going to do is go to Data, Weight Cases, and then you're going to click on the frequency variable. You're going to say weight cases by, and you're going to move it into this category here, and then you're going to just click OK. Then that tells SPSS just to remember which variable actually contains the frequencies to use. Now what we're going to do is actually run the chi-square test. So if you look here, the general process starts with us just doing crosstabs and a contingency table. So the way that we do that is coming here, going to Analyze, Descriptive Statistics, then we're going to come down to crosstabs. The next thing we're going to do is make sure we select just one of our variables of interest, and we're going to drag that into the box that's labeled row. And so for this example, I'm just going to pick nationality to be a row. Then the next step is going to pick interest here. How do they ride their bike? With hands. and move that into the box labeled columns. Now what I have to do is just make sure I click this chi-square for right now. Expected. For counts, I want my observed, I want my expected. I'll do row, column, and total for my percentages. Click OK. Click OK. Here's like a simple way to look at the data. What I have right now is just a cross tabulation table that's produced in SPSS. I have put it into this column here, and what we're looking at is our counts. So we can see that a total of 137 individuals rode their bike one-handed, which is 87.6% of them being Dutch, right here, being Dutch. And then of the 732 individuals who rode the bike two-handed, 578 or 79% were actually Dutch. The big thing now is, since we know our crosstabs and we see that each of our categories has more than the 5 counts needed to meet that assumption, we can move on and actually do the chi-square test. And so the big thing here that we want to remember is to come into SPSS, analyze, and if you didn't grab everything at first, you just go chi-square. If you want the contingency coefficient, you can grab that. The Phi Kramer, you can grab that too, but you're really not going to need those options. They were ones that were discussed in your textbook. It's kind of interesting for you to see them if you're interested in what the scores are. But as long as you just make sure that you're grabbing your same observed, expected row, column, and total percentages here, you're going to be great. We always just round the cell counts. We don't have to worry about format. We'll just have it go in ascending order, but if you want in descending order, you can have that too. We click OK. It's going to take us to our chi-square table, and this is what we're going to now interpret. So for the chi-square table, I want you to just realize that the value is 5.44, and this value has a two-tailed significance of 0.020, which is smaller than 0.05. Hence, it is significant, and it suggests that the pattern of bike riding significantly differs among English and Dutch people. And so the next step, though, before we write our results, is to compute and interpret the odd ratio. That was for task 6 that we just accomplished. And so with the odds, what we want to understand is what is the odds for doing these different tasks. So for the Dutch writing one-handed, the Dutch writing two-handed, the odds for someone writing one-handed that's English, the odds of someone English writing two-handed. And with the concept there is that it's just a very useful way to measure the effect size for categorical data. And we do these calculations that go back to your table that we first calculated right here. So it's using these counts and doing all the math and creating a ratio. So the odds of someone writing one-handed if Dutch is 120 divided by 578, which we get 0.21. And then we get the odds of someone writing one-handed if English. So that's 17 divided by 154, or it's 0.11. So the odds ratio is the 0.21 divided by 0.11, and we actually get a odds ratio of 1.9. Now this can be easily written up as one complete statement for the results of the chi-square test and the odds ratio. What we would say is that there was a significant association between nationality and whether the Dutch or English rode their bike one or two-handed. And we have the chi-square symbol, so we do the Greek symbol. We have 1 degree of freedom, and then we have written the actual statistic, 5.44, and we must round that to 2 decimal places according to APA style. And then we write P equals 0.020, and we use the exact P value. Then we have one statement about the odds ratio, and we say the odds of riding a bike one-handed for Dutch people was 1.9 times higher than for English people. And we have answered Andy's question for task 6 and for task 7. Now I want to talk a little bit about another way that you can do chi-square tests to compare early to late respondents in your survey data. Non-response error for an online survey is handled several different ways. But one of the most common ways we do in agricultural communications, agricultural education, or in agricultural extension education is by comparing early respondents to late respondents of the survey. And our typical method for identifying the non-response bias presumes that our non-responders are more similar to our late responders than our early responders. So that helps us control for our non-response error, ensuring that our early and late respondents are not different in their ways of answering the survey items. And we use the chi-square test when looking at comparing these two groups to different categorical variables. So here's our situation. I have a graduate student who has successfully defended a master's thesis about the role that farmers played in farm-to-school programming. And this student handled non-response by comparing early to late respondents. The survey was administered between March 29th and April 10th, and the early respondents were categorized as any participant who answered between March 29th and April 3rd. And then all the late respondents were after April 3rd to April 10th. And we actually do a cross tabulation to compare the early respondents to the late respondents. And we picked just a few variables that we knew would be differences for the type of farmer that would participate in farm-to-school programming to see if our respondents are different. And we looked at gender, we looked at the years of farming, and we looked at their age. And it's important to know that when we first did our crosstab table, we didn't have 5 counts for every single category. And so you're allowed to recode variables. So we did the length of farming as either 0 to 17 years or more than 17 years. Then we recoded age as 18 to 50 years and then 51 years and older, knowing that the average age of the farmer is in that later category. So we wanted to compare the US average age of the farmer to those younger farmers. And then we wanted to look at gender being just male and female. And our p-value was compared to the significance value, and we had an alpha level that was 0.05. And if our chi-square test is less than that alpha level, then there is significance between the early and the late respondents, and that is not good. Because that means they're not consistent in that we're thinking about, how our non-responders to our survey are supposed to be like our late responders. Well, if our non-responders are different than our early responders, then we're not going to be able to handle that non-response bias. So you want to just keep that in mind when you collect your data. Let me demonstrate how this is done. So in SPSS, I have the data file, and we actually add a variable into the SPSS that is coded as either early respondent or late respondent. And we gave an early respondent a code of 0 and a late respondent a code of 1. So those are our values, our label values. And we could consider what the label would be based on the end date for when the respondent actually completed the survey. And when you run these chi-squares, I can put in, was the respondent an early or late respondent? And then in the column, I can scroll down, and then I'll do this for just one of our variables, and I will do it for gender right here. What is your gender? I'll make sure my statistics chi-square, cells, expected, my row, column, and total percentages. I'll compare column proportions. I'll adjust the p-values. Hit continue. Format. I'll keep it ascending. Click OK. And what I'll do is I'll go into our PowerPoint presentation now and actually show you how I interpreted all the data here. And so here's the contingency table for the demographic characteristic of male versus female and whether the people were early or late. And we just double checked our expected frequencies. And you see the expected frequency count here. Slightly off just based on how the graph moved. But you'll notice that none of the categories are 5 or less. So I'm not really worried. Our percentages are good too. So we can move on. We know we've met that assumption. Then we're going to look at the chi-square test table, and we do not want a significant value for our Pearson's chi-square. And we have 0.645, and that is not significant because it is greater than 0.05. And that's a good thing. It means our respondents are our early and late respondents are not different. We looked also at year length of farming, and we looked at it as 0 to 17 years right here. We looked at it then at more than 17 years. First thing you're going to notice is that we have enough counts for all the categories, so we don't have to worry about that. And we've met that assumption, so we can look at the chi-square test. Here we have a chi-square value of 0.533, which is greater than our alpha that we set at 0.05. So we do not have a significant value, which is good in this situation. Then lastly, we looked at their age. And if you look at this, we'll see our count. It is certainly meets the criteria also of the 5 counts per category. And we just had our age as 18 to 50 and then 51 and older. We look at our chi-square. We see that is 0.549, which is greater than that 0.05, so it's non-significant. That's important. Now we got to write our results. So if you are writing a master's thesis or a dissertation, you would state that a total of 143 online surveys were completed, and that non-response error was accounted for by comparing early and late respondents, that the response were divided into early or late respondents once the first reminder email was sent. And then, so, April 3rd, and then everything after April 3rd. And then the chi-square testers reported to compare the early and the late respondents in their gender, or length of time farming, and the age. And that the length of time farming was recoded as 0 to 17 years and then more than 17 years. The age was also recoded as 18 to 50 years and then 51 years and older. That the p-value was compared to a significance value, and an alpha level of 0.05 was used. If the chi-square test is less than the alpha level, then significant differences exist between our early and our late respondents. And as shown in Table 3.1, no significant differences were found between early and late respondents. And then we have to create a table that follows APA style. And we need to say demographic characteristics of early and late survey respondents. And we have our two columns. We have our late respondents and we have our early respondents, and we do our frequencies. So you have your N and you have your percentage. This variable right here is your chi-square, and this is your p-value. And you have to be able to indicate your dichotomous variables. So you have gender, and you break it down into male and female. You have your years farming, and you break it down into 0 to 17 years or more than 17 years. And then you have your age. It has to be 18 to 50, and then 51 and older. And if you can include all of that right up, as well as your information for the table displaying all the text, you have met the criteria for what you need to report when handling non-response rate for a survey. This is a great way to see how applicable the chi-square is in our research practices. But in the event that you have really small samples, your approximation is not going to be good enough, and so you might need to do a chi-square distribution that does the Fisher's exact test. And the process is pretty much the exact same. You just interpret the Fisher's exact test score rather than the person's chi-square test. There are other measures of association I want you to be aware of in your research. You can choose to use the phi coefficient and the Cramer's V coefficient in your research, and they're measures of strength of association between two categorical variables. And your phi is used with a 2x2 contingency table. And then your phi is calculated by taking your chi-square value, and then you just divide it by your sample size, and then you take the square root of that value. And then you can also, if one of the two categorical variables contains more than two categories, then you can do a Cramer's V, and that's preferred to the phi because the phi really fails to reach its maximum value of 0, or its minimum value of 0, which indicates no association in these circumstances. So if you have categorical variables that contain more than two categories, you can actually interpret the Cramer's V, and then you can run a similar test. Now, these measures of association are very briefly discussed in your textbook. But here's a great contingency table I use for determining my categorical variables when they're nominal or ordinal and what test I need to run. So if I have a dichotomous variable, I'm comparing it to another dichotomous variable, I could do a phi coefficient. If I have a dichotomous variable and I'm comparing it to a multichotomous variable, I can do a Cramer's V. Notice that this is not something you can do because, like log linear, you have to have all of your variables be 3 categories or more. Sometimes that's not the case, like with early to late respondents, you only have 2 categories. But you might have a multichotomous variable you're comparing your early to late respondents to, like marital status or political party. And so you could use the Cramer's V statistic. And when you have multiple categories for your first variable and your second variable, you can do Cramer's V. And then if you have any questions or comments about using the chi-square test or analyzing categorical data, please contact me at kelsey.hall@usu.edu or through Canvas inbox.